In the third part of section 7.2, we'll discuss how to compute the singular value decomposition. Matrix A in n by n dimensions is given. And first we form A transpose A, the covariance matrix of A, and find the eigenvalues and eigenvectors, lambda 1 to lambda n, and v1 to vn. You can make the matrix orthogonal. That means here eigenvectors are here orthogonal each other, and then the norm is 1, so that V transpose V is identity. Now we sort the eigenvalues to their magnitude, and then take a square root to get sigma j. And so here, that is V, and collection of sigma j will make a sigma. And then here, from this algebraic equation, and now 1 over sigma j, avj, becomes uj. So we're done here. So once it's required, then we can pick up some remaining columns of u. We consider this one as full SVD. Okay, then now full SVD is given in this way from u to ur and un. And now here, in diagonal of there's a sigma metric, sigma 1 to sigma r. Assume right now there's a rank r, and these are V transpose. So we're done. Here we have a theory. If A is symmetric, and m by m metric, and square and symmetric, the reason we are considering this lemma is here. A transpose A is an m by m metric and symmetric. So for A transpose A, now the properties in this lemma hold. Okay, and then A is square and symmetric, then all the eigenvalues are real, and eigenvectors correspond to distinct eigenvalues are orthogonal. That means that once two different eigenvalues, okay, for example, now let's say lambda 1 and lambda 2, now, okay, lambda 2, and they are not the same, and the corresponding eigenvector is v1, and that is v2 for here. Then here v1 dot v2 is 0. They are orthogonal, and you can prove that, and I gave you some hints, and try to solve the problem. In exercise 4, you can try. Okay, let's deal with one example. Find the SVD for A. Here's a 3 by 2 matrix. And first we form A transpose A. Now try to find here eigenvalues and now eigenvectors. And if you do, then lambda 1 for that metric is 18, and lambda 2 is 5. And here for lambda 1, you can find v1 and v2. Now normalize, and then you can recheck that. So we finish the V metric, right singular vectors. Now here, lambda 1 is the largest one. So it's sigma 1 is square root of lambda 1, and sigma 2 is now square root of lambda 2, so that the matrix sigma is given in this way. Okay, V is given here. Now sigma is made. Now here one of sigma 1 and AV1, which is U1, you can get here by using the computer algebra system. I try to get the exact value. Okay, U2 is 1 over sigma 2 AV2, and that is the result. Okay, now so that here A is U sigma V transpose, and this is U and sigma, that is V transpose. Of course, here if you practically multiply, then it will recover the original metric A. Okay. Now here we try to find the pseudo inverse of A. Pseudo inverse of A plus is V sigma inverse U transpose. The same metric A here. We are dealing with the same metric. Okay, for that one, already we got in the previous example, and this decomposition, singular value decomposition, so using the matrices, we can get pseudo inverse of A. So we reach at that one. Okay. Okay. In practice, the singular value decomposition is computed in this way. So the way of getting singular value decomposition we considered is a classroom technique. If you do by using your hand, then you can do it in this way. But in computer, it is implemented in this way. That is based on Gallup range contribution. First, we try to change the metric into bidiagonal metric, and then by using the QR iteration, we try to get an eigenvalues and eigenvectors, and then here this transformation is orthogonal transformation, and so that after getting eigenvalues and eigenvectors, now transform back for the original metric. That's the idea. Now this transformation is not so much complicated. By using your household reflector transformation, you can get that one quite easily. And then so that here there is orthogonal matrices are multiplied here in front and back, and here you can get this bidiagonal metric. And for this bidiagonal metric, the QR iteration works very effectively to get here the eigenvectors and eigenvalues, and then here now and transform back for the original metric. It's very efficient. And even though and dimension is larger than 1,000, and you can get it almost instantly. Very efficient and stable algorithm. Their contribution to the society is really really very good. And then we have to thank them for their contribution. Okay, here the algorithm is extremely stable and also extremely efficient, and computational complexity for the computational whole is given in this way. And in modern computers, you can do it very quickly. And now here you can use it, and for instance in Python and NumPy linear algebra package, you can find SVD, and in MATLAB or Maple you can use just SVD. Now if you are using Mathematica, then the name is a singular value decomposition. Okay. Now here, and we consider the rank of given metric. Once there's no rounded error or noise or uncertainties, then here the SVD reveals the rank of the metric quite clearly. So it's 0. Once it's now rank R, then only R singular values is positive, and the remainder part will be 0. But unfortunately, here and some errors and also now round of error are involved in the computation, so that determining the rank is problematic. For example, we consider this metric, and first column, the second column, and addition of these two columns is now third column. So that obviously the rank of metric A is 2, because only we have 2 independent column, and then now here the third one is now addition of 2 columns. Okay, if you're using for instance MathLab SVD, even though you're using Python, it'll be the same. Here we have first one, sigma 1, sigma 2, and sigma 3. Now, along with this one, we have to decide of the rank of A, so that is 2 or 3, but which one is the right one? And we have to decide. And in order to do that, we need a threshold. Now, is very small, so that you may say is rank is 2. But what if sigma 3 is around 10 to the minus 3? Then can you say the rank is 3? And we have to have some guideline for the determination of the rank. Okay. So here, and usually in software, numerical rank R is decided with a threshold T. Like in this equation, sigma 1 to sigma R is larger than T, and from sigma R plus 1, they are less than or equal to T. Then here, the output will be R. By using this threshold technique, it is decided. Now, how can we decide this threshold? In here, MATLAB, and also in NumPy, and that in Python, it is implemented mimicking MATLAB in many cases, so that here in Python is the same. In MATLAB, rank command is deciding along with the threshold in this way: 2 times maximum of mn, so that this is the dimensions of a matrix, the metric, and epsilon, that is unit round of error, and then here a 2 norm. Okay, a 2 norm is, we already know that this is same as the largest singular value, sigma 1. Okay, so let's consider what it is. And here, that epsilon in MATLAB, by using EPS, you can get it. It's the same as 2 to the minus 52 in double precision. So that is about this quantity. So here, for this metric, now m is 5, n is 3. So the maximum of 5 and 3 is 5. Okay, so the 2 times and 5 and epsilon here, and then for the matrix sigma 1, the A2 norm is this one, and after multiplication of that, we can get the threshold here, 5.77 times 10 to the minus 15. So that one is smaller than that threshold, so that rank must be 2. Okay? Okay, that's the end of the third part. Thank you.